Welcome. So, this is an online course on quantum computation. So, we begin with the Dirac notation. Paul Dirac introduced the notation now known as the Dirac notation to write down wave functions in the form of vectors. So, if you have a function, wave function psi, it is written using this bracket symbol. It is referred to as ket psi, and its conjugate psi star, since wave function psi is a complex number, is written the other way around. It is called Bragg psi. Now the normalization condition that psi star psi integrated should be equal to 1 is written in this fashion: Bragg psi and ket psi. So together it is called bracket. This has to be equal to 1, which is the normalization condition. So the normalization condition in terms of the Dirac notation is written as Bragg psi and ket psi, which is equal to 1. And any expectation value of a quantity, say q hat is the operator corresponding to the observable, then the expectation value of the observable is written by sandwiching the operator between Bragg psi and ket psi. The general solution of the Schrödinger equation is the linear combination of all possible wave functions, and in the Dirac notation it can be written as psi ket psi is equal to c1 psi 1, c2 psi 2, c3 psi 3, and so on, where psi 1, psi 2, psi 3 are each solution to the Schrödinger's equation. So the total solution is a superposition of the individual solutions, a linear combination of them. So this is referred to as the quantum superposition. In general, a particle can be interpreted to be in a superposition of all possible states. After the measurement, the superposition collapses and the particle is found to be in the ith state. For example, it could be in the state psi 1 with probability modulus c1 squared, or it could collapse to the function psi 2, and it could be in the state psi 2 with probability psi 2 squared, and so on. Now let us understand the quantum superposition with uh, the with an example, a thought experiment conceived by Schrödinger. So this is referred to as Schrödinger's cat thought experiment. So the experiment involves putting a live cat inside a box with a radioactive material and a pile of poison, say cyanide, and a detector. So how does the experiment work? So we don't know before whether the radioactive material is going to decay or not. It is a probabilistic event. The radioactive material may decay or it may not decay. If it decays, it is going to release the poison, and the cat is going to die. Or if the material doesn't decay, the poison is not released and the cat stays alive. So a living cat is put inside a box with a small amount of radioactive material, and the box is kept fully isolated with the outside environment to make sure there is no interaction from the outside. So the amount of radioactive material taken is such that an atom in the sample may decay or may not with a 50-50 chance. The decay of radioactive sample is a probabilistic event. We cannot tell in advance whether the sample decays or not. If the sample decays, it sets off the Geiger counter, which will further release poison and the cat will die. If the sample does not decay, nothing happens and the cat lives. Now the question you ask, is the cat dead or alive? So quantum mechanically, the answer according to quantum mechanics is the cat is in a state of both living and dead simultaneously. This is because of the superposition principle. The state of the cat inside the box can be written as cat is equal to 1 by root 2 of cat alive plus cat dead. So the factor 1 by root 2, the square of the wave function represents probability. So when you make a measurement, you square 1 by root 2, it is 1 half. So there is 1 half chance that the probability of the cat is alive, and there is 1 half probability that the cat is dead. So even though the cat is in a superposition state of both alive and dead, when we open the box, that is, we are measuring, the opening the box is the measurement, we see only one outcome. Either it is dead or it is alive. So the very act of measurement is forcing the quantum system to one state. When the measurement is made, the wave function collapses, and this is referred to as the Copenhagen interpretation by Niels Bohr. Suppose we see that after opening the box, the cat is alive. Quantum mechanics tells that both outcomes occur with the same probability. So, what happened to the other? Well, the reduction of the wave function is not explained by quantum mechanics. So, this was improvised by Hugh Everett in his many worlds interpretation, saying when a measurement is made, the worlds split, and in one universe, if the cat is alive, in the other, it's dead. So, both the possibilities are taken into account. So we note that in this thought experiment, no cat was harmed during the experiment. It is just a thought experiment. Of course, the cat is not in a superposition state in the box because the quantum effects can be ignored in the macroscopic world. The example of cat was given to clarify the idea of superposition to an ordinary person. But the quantum superposition is very much true in the quantum realm. Particles can exist in simultaneous states at the same time. So let us consider a realistic example. So this is an example. So an electron which is kept in a magnetic field can have two states. Either it can be in, say, a spin up state or in spin down state. So an electron kept in a magnetic field can be spin up or spin down, or in a superposition of both spin up and spin down. So the spin state of the electron is written ket chi is equal to A spin up plus B spin down. So the Copenhagen interpretation says when the measurement is made, the wave function collapses. It is found in either spin up state or in spin down state. Before the measurement, it was in a superposition of both of them. In the many worlds interpretation, one universe, the electron is in spin up state, in another, it is in the spin down, and so on. So, when a measurement is made on the electron, the probability that the electron is in the spin up state is modulus A squared, and the probability that the electron is in the spin down state is modulus B squared. And we have the normalization condition because they represent probabilities. The sum of probabilities must be equal to 1. So mod A squared plus mod B squared has to be equal to 1. So suppose you have two particles, then how do you write the Dirac notation for two particles? So far we have considered only one particle, but if we want to study two particles or more, then what will be the wave function of more than two particles? I'll just give you the notation without explaining too much into it. For a single particle, we just write get psi. For two particles, let us say if particle was 1 is in the state psi and particle 2 is in state phi, then the wave function of the two particle system is uh, get psi, get phi. There is a tensor product between them, but you don't have to worry about that here. So the same procedure for higher number of particles, you just write the state of each particle next to each other. Now let us understand quantum entanglement, another phenomena seen only in the quantum domain as a non-classical feature absent in the classical world. So we shall understand the concept of quantum entanglement using an example, not in a generic sense. There is a particle called the neutral pion. The neutral pion is short-lived and decays into electron and positron. So pi 0 is the neutral pion, so it decays into electron E minus and positron, which is the antiparticle of electron. The spin of the neutral pion is 0, but the spins of electron and positron is not 0. uh, Electron has spin half and positron has spin half. In order to conserve spin, one must be spin up and the other must be spin down, such that the total spin is 0 because pion had spin 0. After the decay of the pion, we do not know which particle has spin up and which particle has spin down. You could have electron spin up, in which case positron would be spin down. If you have electron spin down, in that case positron would be spin up. The spin state of the electron positron system is given as ket psi is equal to 1 by root 2 spin up for electron, spin down for positron, minus spin down for electron, spin up for positron. It's in a superposition state. The electron and positron need not be nearby. They can be even light years away after the decay. So the electron is on Earth, let us say, and the positron is on Moon. Let someone on the Earth measure the spin state of electron. If the electron is found to be spin up, then even without doing anything to the positron, it becomes spin down instantaneously. If the electron is found to be in spin down state, then even without doing anything to the positron, it becomes spin up state instantaneously. So even though the electron and positron are separated in distance, by measuring the state of one particle, the state of the other particle is affected. We say the two particles are entangled. This phenomenon is called quantum entanglement. We shall use quantum superposition and quantum entanglement to study quantum computation. Let us meet in our next video.